I would like to introduce our first speaker, Dr Federico Perrotta, and he's going to talk about looking at existing concrete roads and how we can model them best for their deterioration. And so we know what's going on beneath our wheels. Thank you.
Thank you, Steve, for the introduction, and thank you, BritPay, for inviting me today. Good morning, everyone. My name is Federico Perrotta, and I'm a consultant at AECOM. So today I'm presenting a novel data-led and performance-based approach for the deterioration of concrete roads in the UK. More than that, I would like to tell you a little bit of a story of a great team, a story of the successful project that was run on behalf of National Highways. Not an easy path. We had ups and downs throughout the project, as when data, engineers, innovations, and other parts come together, it's not easy to put everyone on the same path. But I would say we managed quite well in this case. So again, I'm Federico, and this is National Highways Concrete Road Deterioration Model. A bit of an outline of today. The journey was not an easy path. We will start with an introduction to the problem and the challenges that the client was facing. We will go into the definition of defects and how we collected data, to then introduce you to the approach, model structure, and implementation. So to start from the top, the concrete roads can be found a bit all across the territory of England. But it's a very small percentage comparing to the whole network that National Highways manages. In fact, it's just 4%. Probably because of that reason, they haven't been the primary the priority for many years. And as they come to the end of their residual life, these roads, because of different reasons and probably because of the low need of maintainability or maintenance through their life cycle, people had just thought that they would last indefinitely. As for today, we are looking just at legacy concrete pavements, which are defined as those pavements with exposed concrete, with a surface of exposed concrete, or with maximum 50 millimeter of asphalt layer on top. We can consider these pavements as a single group because the asphalt overlay really doesn't make a contribution to the structural behavior of the concrete. So we can model them together. Why it is important to model these assets and why it is good to model them correctly? Because again, low maintenance requirements, little information collected, and it is difficult to make decisions. It is difficult to plan for how much funds are needed to keep these roads, these key assets of England running. So as the roads tend to get towards the end of life, they tend to suffer issues, and they tend to get defects on the surface. And this is a bit, you will see, is a bit where we will go with the modeling, trying to understand what type of defects appear on these roads, trying to understand what the condition of the pavement is, and really with all the data that is collected, develop something that reflects current and historical trends. But let's start from the standards. So DMRB clause 226 is probably our standard for pavement design. And this is historically include direction of also how to calculate residual life based on RR87 model. This has been used for many years, again, to calculate residual life, but residual life, the concept of residual life, especially for concrete pavements, rarely reflects what the condition of the network are. In fact, running a little exercise and collecting a condition of the network recently in 2022 and comparing that to what RR87 was predicting in terms of residual life for the pavement, we saw that there was little correlation to what the current conditions, to what, again, residual life was. And this is because of many reasons. Design assumptions were done years ago when perhaps we didn't have this progression of traffic. Climatic loads have changed over the years. There is a lot of complexities that design models cannot account for. Similarly, we performed a similar exercise also with international models, so AASHTO 93 and AASHTO 2008. But again, being these models based for design purposes, they don't quite reflect reality. So what are the main challenges that the client was facing? Well, first of all, there is obviously a safety concern. It's not safe to have workers or walked inspections on the road all the time. So if we can find a way to actually collect data and manage data appropriately in a way that we can make decisions based on a digital platform, that would be a great achievement. And definitely technology is not anymore a challenge, but it's probably our opportunity. So there is plenty of technology out there that nowadays collects data in various ways. I mean, probably a lot of the accessories that we wear every day present a lot of sensors and a lot of technology that measure some indicators about our health, about other things. But mainly in this project we used some camera developed by Trimble that was able to detect defects on the pavement based on video surveys. On top of that, obviously, we have all the data that is collected for routine maintenance and for routine monitoring of the network, which again included tracks information, scanner, screen, etc., etc. However, for this topic, we identified that the historical data that was in the PMS was not really giving us clear trends. So we wanted to identify an easy way, a simple way to define a condition of the pavement, which was allowing then the client to make decision on what type of treatment was going to be performed and how serious the problem was on the pavement itself. This is why we separated defects collected by the AI into categories. The number of cracks per 100 meters and the number of what we call the damage, so the count of any other defect that is not a crack, in a separate indicators. Again, here we have some example of some of the defects that we encounter at network level. And these were definitions of the defects based on what the survey technology was back then when we developed the model. Now there has been some development, so we are looking also at improving these definitions, but again, it's a work in progress at the minute. So the model structure By analyzing the amount of data that we had, we realized that a sort of parabolic shape of our curves was actually fitting our data best. We looked at the information we had available, and we had some design parameters, but also some actual information, such as the age of the payment itself, the traffic, the yearly traffic, the slab depth, etc. In line with engineering judgment, we determined that the correlation of these parameters to the number of cracks per 100 meters and the number of the rest of the damage per 100 meter was giving us the highest, the better results. So we fitted this parameter into two different equations. And again, the fact that we have two different equations, one for crack and one for damage separately, allows the client to understand that these two parameters may deteriorate or may change over the life cycle of the payment differently. And this allows them to plan for what sort of maintenance interventions are required. Because again, a crack may require sealing, but perhaps some punch out requires a different type of treatment to be repaired. So this is a bit how the developed curves look like. They tend to have a steeper shape when traffic increases or when the slab depth is sort of smaller. And this is because, sorry for coming back to the previous slide, but this is because slab depth is sort of at the lower part of the ratio, while instead traffic and age of the payment are on the upper part. This make, again, the curves having this non-linear shape. And this reflects what we have seen on hundreds of 100-meter sections all across the UK, some in better condition, some in worse condition. And for modeling, we actually considered that those cracks or damage that were repaired were also part of the historical degradation of the payment. So at a regression analysis stage, we decided that the repairs had to be part of the equation. While instead, when this is then used at an operational level, we will calculate what the expected number of cracks and damage are at that point in time. So for example, if now we are on a pavement that has 10 years life and we want to predict what this will be 20 years afterwards, we basically will have to go along the line and say, okay, this pavement is expected to have this many cracks in this many years. In line with DMRB specification and practice, we established some condition categories which were enabling us to determine at what level at what stage of the life cycle the payment was based on the number of cracks and damage. Again, there are similar graphs for different type of payments, one for URC, one for JRC, and one for CRCP. So both for reinforced and unreinforced payments, for jointed and unjointed payments. And similarly, there are different type of equations for bound and unbound foundation. This is to take into account the fact that the lower part of the structure of the payment sometimes have effects also on the overall structural behavior. The condition category are defined as such. Again, it's very much in line with the MRB guidance. So with category 1 that corresponds to a low level of degradation, and category 4 that corresponds to a severe level of degradation. And thresholds were established based on a few criteria. So obviously we started with looking at what was making sense from an engineering perspective. We tried to validate that against the video surveys, And obviously, we wanted to make sure also that these categories were allowing us to deteriorate all the sort of payments that we have available and structure that we have in the UK, like, again, with a good level of confidence. Obviously, we wanted to make sure that the results we were obtaining also in the long term were making sense from an engineering perspective. We haven't used deflectographs type of data in our model, but perhaps it's something that we could explore in future iterations. In terms of implementation, again, starting from validating against current design-based models, we realized that there wasn't much correlation. We use historical data and data collected using AI-based technology to develop our model. We use some data mining technique to aggregate and cleanse the data where necessary. Regression analysis to put together our curves. And once we have our curves, our equations, we can then use them to predict future conditions. At a basic level, we can perform some sort of pie chart and understand what sort of percentage of the network reacts in certain ways over time. And we can also introduce assumptions of what sort of effect treatment has on the lifespan of the payment. But we can implement these equations in a web application that we have developed. This makes really our analysis much more interactive. We can understand what part of the payments require intervention first. We can prioritize schemes. And obviously, we can do that planning this part at the bottom starts saying, okay, this payment tier 0 is in good condition, and slowly it tends to deteriorate. And we can see that different lanes that sort of can deteriorate differently because of different traffic conditions. So results are generally in line with what engineering judgment was expected from national highways. But obviously, without the data to back up that judgment, decision couldn't really be made, funding couldn't be requested. This gives sort of the solid theoretical but also practical evidence that funds are needed to maintain our concrete network. So in conclusions, there are parts of the network with criticalities that require attention more than others. Our model identified those and helped National Highways secure some funding for some work in that respect. The new curves consider current condition, actual loading, and historical trends. We developed a web-based GIS application that allows us to model things spatially, so identify which areas of the network require intervention first. The model is fully transferable and scalable, and in fact, we have been in touch recently at PIARC with a few people to perhaps trying to expand the model and see if this can be applied to different case studies. In particular, also with some colleagues in Europe. So this was me for the moment. If there is any question, I hope I didn't take them.
Please speak now, hold your peace, or Federico later.
Yeah, please.
Just wondering if there's any correlation. Thought I'd talk loud enough anyway. Hello. Is there any correlation or relationship between the cracks that are appearing in the different phases, the 1, 2, 3, 4 categories, based on location, geology below, and the construction, obviously, because obviously in the east you have different soils to the southeast, northeast, aggregates might be different below. Did you come to any conclusions whether there was a better part of the country than another, or a better construction that was taking place?
So this is a very good question, and definitely there might be local conditions that affect specific behaviors at network level, but this was a bit out of scope of our modeling, in a way that we tried to develop something that was applicable for a network level analysis, so and a scheme level analysis, saying in these conditions, on average, things should work this way. But it's not, we didn't go to the level of detail of saying this payment because, I don't know, because there might be some drainage issue, because there might be some local situation that verifies specifically on that spot of the network, this payment will deteriorate much faster than this other. We didn't go to that level of detail, but definitely it is something that probably with a bit more data could be done. Cheers.
Any other questions, please?
Hi, Will Hellier from Atkins Realis. It's a question around, I suppose, the validation of the model. Obviously, it's good looking at the history and kind of getting the model developed based on what has happened in the past. How much validation have you done in sort of validating that against real life performance, and is it too early, or are you monitoring that going forward?
So the minute obviously is difficult to, another really good question, because it's difficult to validate really a prediction model based on the fact that future hasn't happened yet in a way. But what we are planning to do, and this is a bit what I briefly touched on, like we have other type of data set that could be looked at. Again, deflectograph was one, but GPR are other type of information that are in the sort of data set, and this perhaps could be used to validate the information, to validate the performance of the model against the different type of information that have been considered. Whether that will give us a clear understanding of whether the model is performing well over the next 10 years, I think that's a sort of iterative process. So the model, as it is structured at the minute, has been done based on regression analysis from data. So perhaps by collecting data in the following years, we could, this year and next year, perhaps we can start identifying if the model is following the sort of actual trends, or if it is following something else. If it is not following the actual trends, perhaps the data can be used to rerun sort of the regression analysis to adapt the curves to the actual trend that we observe at network level. I don't know if that answered the question. Yeah. Cheers. Thanks.
Any other questions, please? No. Federico, thank you very much.
Thank you very much.